Hello and welcome to this complimentary webinar with the title Hierarchical Modeling for Zoom In, Zoom Out Multi-Block Data Analytics. My name is Lennart Eriksson. I work for the data analytics business that is part of Sartorius Stadium Biotech. The roots of our business go all the way back to 1987 when Professors Svante Wold and Rolf Karlsson founded a company in northern Sweden, initially called Umetri, which later became Geometrics, and these days Sartorius Stadium Data Analytics Solutions. And today we're lucky to have Professor Johan Trygg on board to continue drive the innovative efforts. Our mission is driving growth by enabling our customers to see what others don't, and our vision is to be recognized as the leading data analytics solution provider. Now, turning into the components of the Geometric suite of data analytics solutions, we can say that it comprises 6 software solutions. We have the model software for design of experiments to get the data right from start. We have Easy Analytics, which is aimed at facilitating everyday data-driven decisions in an efficient manner. We have the Simca software, which we can say is the flagship. This is for multivariate data analysis and building models offline. And this is also where today's presentation will take place. In addition to that, we have the online and real-time extensions to the Simca software. We have Simca Online for real-time deployment of models developed in the Simca software. We have Control Advisor for obtaining a recommended future. And then we have Active Dashboard, the interactive performance insight web-based solution. So going into today's topic about hierarchical modeling, we can see the contents here. First of all, we will have a little introduction. We will then zoom in on the topic of today. We will look at the working principle. We will take a look at what we mean by the zoom in, zoom out possibility. We will view how hierarchical modeling is enabled in the Simca software. When we are forming hierarchical models, there are different options for the so-called hierarchical base variables. Whenever we are starting or launching hierarchical modeling, the result will be that we are forming new data sets, and for that matter we also will look into the workset dialog where we decide from which data sets to pull out the data to make up the foundations for these hierarchical models. The main illustration is a spectral data set called Karaginans, taken from our series of tutorial examples in our training material. It is the Karaginan data set that we will demonstrate, and then we will return at the end into the PowerPoint for a couple of final slides with summary and conclusion remarks. There will also be possibilities for a Q&A session at the very end. So if you have any questions, please type them in the question tool throughout the presentation. So as an introduction to this topic, we can say that multivariate models involving large number of variables are often difficult to overview and interpret, and one of the obstacles is that primarily the loading plot becomes very, very crowded, and it can be like a jungle with points in the loading plot, making it very difficult to understand what we are looking at. And one of the risks to try to work around that situation is that there can be a temptation to start to eliminate variables in order to make things easier to overview. But there are risks with that, and one of the risks is that you will lose important information, and you may also lose in efficiency in the data analysis. And then usually a better alternative is to divide the data into blocks, smaller blocks of variables where the variables have a logical relation between them. For instance, that they are created based on the same generating background mechanism. And another positive asset with this is that it also enables blocks of different sizes to be better accounted for and better balanced. Before we go into more details and where we are and more details and looking into how things are implemented in the Simca software, I just want to show you this plot right away, trying to point out where we are heading in this presentation. So the plot I'm pointing to now is a loading plot arising from a principal component analysis model. And right underneath it we have the score plot from the same model. The points here are different so-called GPCRs, G protein coupled receptors, and the descriptors are descriptors of the amino acid sequences of these amino acid sequences. In the right-hand part, we see a similar model or an alternative model for a similar data set where we have used the hierarchical modeling approach. There are different things to see here, and first of all, one of the things to realize is that when we are comparing the original principal component analysis model with the alternative hierarchical model, we see that there is no change as far as the distribution of the different observations is concerned in the score plot. So whatever we have done between these two models, there is some stability. The other thing is that the loading plot arising from the hierarchical model is much simpler to interpret. There are much fewer variables that are active. Over here we have around 600 variables, and over here we have around 15 active variables. So we have reduced the number of variables quite considerably. So it means and indicates that in case you have very cluttered loading plots, you can get a cleaner situation, if you wish, in the corresponding loading plot of the hierarchical models. And this is one of the driving forces. So this is where we are heading in the presentation. Continuing now on the introduction and looking into different applications where hierarchical modeling can be of relevance or even recommended are the following. First of all, we have process modeling, both continuous processes and batch processes, and primarily batch processes then on the what we call the upper level, the batch level, where blocks may correspond to variables measured at different parts of the process. Other applications involve spectroscopic applications where blocks may come from dividing a certain spectrum into spectral windows or sections corresponding to different chemical and physical information, or it can also be for the same set of samples, spectra that are acquired using different instruments or different instrumental techniques. Another application area is QSAR modeling, where blocks might be related to different chemical probes in 3D QSAR or different descriptor generator packages, or maybe just as simple as 2D descriptors, 3D descriptors, and so on and so forth. And more recently, we have also seen a lot of block formations in data sets arising from if we put it in a general word or jargon word, within the omics disciplines. And there can be, for the same set of samples, measurements arising from different measurement platforms. The basic workhorses in the SIMCA software, and I then refer to PCA, PLS, OPLS, and O2PLS, fit very neatly into the hierarchical framework. You can invoke any of these models in a hierarchical model. And at the base level, we are then, as you will see in the next coming slides, going to extract very detailed information from the different blocks, regardless of whether we are using PCA or PLS and so on and so forth. When we are going up to the top level, we can then choose to either go up with the scores or perhaps residual variables, and they are then analyzed the usual way. So here we see a more schematic representation of the working principles. So we see in front of us data where you may have block formation in the X part, but also block formations in the Y part. You can have block formations in both X and Y, that's the point here. You can then calculate local models for the individual blocks. It can be a PCA model or a PLS model or an OPLS model or an O2PLS model for the different blocks, and extract the number of scores and loading vectors summarizing the information in each sub-block. Then when forming the top level, you are pulling out usually the score vectors from the different models on the lower level, and these score vectors are then used to form an upper level X block, which we just tentatively depict R here just to distinguish, but it they will have an X character, so to say. And similarly, you can extract one or more score vectors from the different models of the different sub-blocks on the Y side, bring them up to the top level and concatenate them in a Y-type top-level matrix that is here just depicted temporarily as S. So on the top level, conceptually, you have one or more score vectors from the different base level models, and you can then combine these two top-level superscore matrices using a PLS model or an OPLS model. So in this way, the lower level models will zoom in on the detail of every block, and on the top level you will more be looking at the information from an overview point or a vantage point of view. And this is what we mean with the zoom in, zoom out. So the base level allows zooming into interesting subsets of data, and zooming out we have the top level where we're more looking at the superficial information. And I emphasize that this description is just a schematic. Of course, you may have more than 2 layers in the hierarchical chain of models or the hierarchical web of models. You can have 3 levels and 4 levels. One process example that we're using in our trainings relate to the dataset called PROS1A, and here we have a block formation on the X side according to what type of variables they are or which stage in the production they are related to. So we have one X block that is related to input and feed. We have a second X block that is related to reaction conditions, and the third block related to a later purification step. And here we are using local models to model the individual local blocks and pulling out a number of score vectors. We're pulling out 3 score vectors to represent the variability in each of these 3 sub-X blocks. On the Y side, there is a distinction between 2 very important Y variables that have the labels Y6 and Y8, and then there are 6 Y variables that are less important, that are actually compacted a bit using a local model for that subset. We are then going up to the top level with scores for the PSA model of that block, and alongside those score vectors we are actually reusing the original Y and important Y variables. So one of the points I wish to make with this illustration is that you need not only work with score vectors in the hierarchical setup, you can actually align original important critical qualities alongside score vectors. Now we are going to look at the implementation in the Simca software. So here the graphic shows what we call a project window, and you can see that in this project window we have 15 or so models, PCA models and PLS models with the usual detailed statistics. One of the important things to make hierarchical modeling setup transparent is to make use of good titles of the models. And if you have compact titles with lots of information, it will be easier to interpret the resulting hierarchical models. So whatever you're writing here in the title field will be reproduced when naming the hierarchical variables that will result. The critical thing here to enable or enter into the hierarchical scenario is to right-click the model that is currently highlighted, and when you are right-clicking you have an option to select hierarchical base model. When you're selecting that choice, the uppercase letter B, beta, will be turned on, signaling that this model is part of the base level. Later on, when you develop the next layer, any model making up the top level will have a T, and I will show you in the demonstration how to accomplish that. And sometimes models have a duality to them, meaning that they can be both a base level and a top level, and that occurs when we have 3 or more layers. So when you are clicking and selecting this choice hierarchical base model, then what will happen is that this window will open up where you're going to specify how to form or define the super variables, the hierarchical base variables to be used. So as I've said on previous slides, All the basic methods can be part of a hierarchical model, and depending on which model you are currently working with and invoking into the hierarchical scheme, different choices are eligible. In this example, this illustration on this slide, this window arises from a PCA model, PCA base level model, meaning that the only two choices are going up with the scores or the residuals or both. If you are working with OPLS and AutoPLS models, there will be more choices, and that you will see also in the demonstration. So when you have selected what information you think will be part of the hierarchical model and click OK, Simca will create a new data set. And here we see an example where we have several hierarchical models underpinning new hierarchical data sets. The dollar sign is something that is generic for Simca to use when there is something constructed by the software. And this can also happen in other contexts. So the dollar sign here means that this is a variable or it is a data set created by the Simca software. This data set is like any other normal data set that you have imported into the Simca software. You can view the data, you can plot the data, and you will also work with these data sets in the workset dialog when we click on the new button by specifying from which data sets to pull out the data for the upcoming model. Here we then have the workset dialog for a set of score vectors that have been included into the hierarchical setup, and we again see dollar. So the dollar sign as part of the name of each variable, that was because it is generated by Simca. M9 means that it was model number 9 that we're pulling data out of. T1 is the first score vector, and then we have the name for the model that we are pulling the score vectors out of to enable a more transparent understanding of how we are building the models. Apart from that, there is no real difference between, let's say, regular variables and score vectors of this type. It means that we can set their roles as X and Y. They can be scaled, centered, transformed, manipulated in the usual way, like for any variable that we have imported. And we will also discuss that in the demonstration. So this is, so to say, where we are heading. Again, a reminder what we hope to accomplish with hierarchical modeling to simplify primarily the loading plot and make it easier to interpret. And I think I said in the beginning when I was pointing to the loading plot that each point is a GPCR, but of course it is down here in the observation plot, the score plot, where the GPCRs are. When I was pointing here, it was the individual variables I was referring to, but I think I made an error earlier in the presentation. Now I have corrected that at least. A little introduction into this Carrageenan dataset. As I said, it's part of our tutorial examples in our course compilation, so you will find more information there. So basically, Carrageenans are things that you can extract from seaweed harvested from the bottom of the ocean floor. They are used in as gelling and thickening components in food industry and also in pharmaceuticals and cosmetics industries. And in nature, there are 5 different varieties of carrageenans. They are called, the 3 most occurring are called lambda, kappa, iota, and then you have a version 4 and 5 that are called mu and nu, but they are found to much lesser extent in nature. And for instance, if we look at the lambda and kappa and iota varieties, they differ in terms of how many sulfate groups they have per disaccharide moiety in the carrageenans. The example that we're working with has an original literature source, which is this one, carbohydrate polymers. And in this article, the researchers were using mixture design to induce systematic changes in among these 5 naturally occurring carrageenan types. So they were doing DOE varying the nominal content from 0 up to 100% for those varieties occurring in large proportions, and mu and nu were varied at more restricted ranges to reflect their natural abundance or the real proportions. So for these 128 powder samples that were accomplished using DOE, 3 spectral techniques, NIR, IR, and Raman spectroscopy, were used to measure spectra. There are many different data analytical objectives for this data set. First of all, you have the multivariate calibration trail, where you look into the possibility of using the spectral information just to modeling and predicting the different levels of the 5 analytes. An alternative and perhaps also intriguing question is more the data fusion thing that we are going to look into in this presentation. Are there any overlapping spectral information? Will there be unique features for the different spectroscopic techniques? And this is something we will try to answer using the hierarchical approach. Here we see the spectral data after SNV filtering, standard normal variate filtering. Here we have the NIR data, which make up 700 variables. It is in the 1100 to 2500 nanometer range. In the middle we have IR spectra, also pre-processed using SNV, and in the right-hand part we have the Raman spectra. And roughly simplifying a bit, we can say that we have roughly a 1 to 5 relationship among the 5 spectral blocks. And if we're not doing anything and just co-analyzing all the data side by side, there is a risk that the Raman variables will dominate for purely numerical reasons. So the fact that the Raman block is the widest block makes the hierarchical modeling approach to be of interest. On this slide we see an overview of all the matrix structures and also the fact that there is a division into a training set and a test set. So the 128 samples have been divided as 102 for the training set and 26 samples are preserved for model testing. In this presentation we will not show any results relating to the prediction set, but the data are there. We will then calculate 3 so-called base level models. The first base level model is NIR versus the Y. The second model is IR versus the Y. And the third model is Raman versus the Y data. And I just repeat what I said, that the Y block is the different proportions of the constituents encoded by the design of experiment approach. So there will be a number between 0 and 1 for every sample and every constituent, reflecting how much of each constituent occurs in a particular sample. When using the O2 PLS method for the first base level model, we get the 4 plus 2 plus 1 model using the O2 PLS notation, and I refer to another recording on O2 PLS if you want to dig into the details of the O2 PLS. Basically it means that we find 4 vectors, 4 score vectors summarizing joint information between NIR and the Y. So there are 4 components fishing out spectral variation in the NIR data that correlate to the Y data. There are 2 score vectors that summarizes variability that is only found in the NIR data. They are unique to the X part. And then there is also 1 score vector fishing out systematic variability among the samples that is unique to the Y. Similarly, we get the 4 plus 3 plus 1 model for the IR O2 PLS model, and we get the 4 plus 3 plus 1 model for the Raman O2 PLS model. When we are then going up with all these score vectors to the top level, we have two different scenarios, you can say. First of all, we will take the black score vectors. They are 4 from each model, summarizing the variation in all the 3 measurement techniques, correlating with the Y. And we can then use AutoPLS to focus on the Y correlating information. Another trail is then to go up with the red score vectors, summarizing systematic variation in NIR, systematic variation in IR, and systematic variation in Raman that is not correlating to the varied sample properties. And here we can use PCA to focus on the what we call the Y orthogonal variation. So the first model we can zoom in on to is this model, just to see what things look like when we look at across all the measurement platforms, what information are there, is there any overlap between the different spectral techniques, and we also take into account the fact that the Raman will not dominate the model in an undue way simply because it has most variables. There are many plots we can look at, but looking at the 2 first score vectors, the predictive spectral variation, we have the scores to the left, 102 dots because we have 102 samples, and the hierarchical variables. First of all, we have a triangular structures to the samples, and that arises due to the underlying mixture design. Here we have a color coding according to one of the constituents, the lambda. So when we are going in this diagonal from top left down to lower right hand corner, it corresponds to increasing proportion of lambda carrageenans. The coloring in the loading plot is such that the green variables come from the model on the NIR data. The blue variables come from the base level model on the IR data, and the red variables come from the lower level model on the Raman data. There are important contributions from the different techniques related to the different constituents. And interestingly also there, if we just look at one particular block, we can see that the first score vector for the NIR data is very, very important for the iota constituent in an inverse manner. The second score vector of the NIR data is very, very related to the kappa constituent. And the third score vector of the NIR model is very, very correlated to the lambda constituent. And you can continue to work out such interpretations also for the other techniques. Alternatively and complementary, we can also take a look at the variability in the spectra that are systematic between the samples, but the systematic information is not caused by changing proportions of the analytes in the sample mixtures. And what we're doing now is that we will take the 2 score vectors for the top level PCA model and the first 2 score vectors on the orthogonal side for the 3 base level models and just co-chart them side by side. In the top left hand part we have the 2 first orthogonal score vectors for the NIR model. Here we have the 2 first orthogonal score vectors for the IR model, the Raman model, and then we have the 2 score vectors for the top level PCA model. Now whenever inside the CMK software you are arranging data like this and plots like this, if you're highlighting a set of samples in one plot, they are automatically also lit up using the same coloring in all the other open plots that are relevant. We can very quickly see that there is a segregation in the top level model here. There is a division between that set of samples and the samples that are green. And if we're placing a lasso here and marking that group, we can see that that grouping is also expressed by the IR data and by primarily the NIR data, whereas the grouping that we see on the orthogonal side is not expressed by, there is no such structure in the Raman data. Now, because the separation is in the first score vector, it is enough to make a line plot of the top level score vector, and using another color coding. It is so that there is actually it was not due to laboratory restrictions. It was not possible to analyze all the samples at the same day. So there is also day-to-day information that has been used when coloring the line plot of the first score vector here. So this is the first day, this is the second day, and then we see there is a jump to the third day, where after going back to the fourth day, we are more back to sort of the stage or situation that prevailed for day 1 and day 2. So there is a jump when going from day 2 to day 3 and day 3 to day 4, and that jump can be interpreted by using a contribution plot. And if we produce such a contribution plot, we can see that the jump is due to NIR and IR spectra, but not Raman. We have large contributions from the first score vectors, definitely. And the largest and strongest contributor to that jump over the first day is one of the score vectors on the NIR side. And we can then follow up and look at that loading. So now we're looking at the loading PO1 of the lower level NIR model, and it suggests that one of the spectral regions where we have information related to that jump is around the 1970 nanometer region, and that is in the water region, suggesting that this might be some sort of moisture-related problem. The jump over the third day is tentatively interpreted as being part of a moisture problem. Moisture can be a problem in NIR and IR, whereas Raman data isn't as sensitive to such issues. With that little introduction to the data set in mind, we will now go into the SIMCA software and make a demonstration, and whereupon we'll then, after the demonstration, come back to some concluding remarks. I am not going to give any details on how to operate SIMCA. That is part of many of our other recordings. I will just proceed to a regular project. We could create a spectroscopic project because we have spectral data, but since we are more aimed at doing data fusion and data integration and comparison of data rather than multivariate calibration, it is as easy just to work through the regular graphical user interface. The data set has been prepared such that we have the Y data in one worksheet, NIR, IR, and Raman data in separate worksheets of this workbook. So we will then get them imported as separate files. If we start with the Y data, we can see that we have the usual setup for a SIMCA project. We have primary and secondary identifiers for the samples. We have primary and secondary identifiers also for the variables. NIR data, here we just have to assign the wavelength information as the secondary ID. We have another primary ID just to avoid a naming conflict between the different spectral blocks, and that is why we are choosing to have the wavelength or wave number information as a secondary ID. We can't have it as the primary ID because sometimes that can be a conflict, and SIMCA requires that the primary ID is unique. So we will use the again the wave number information as the secondary ID for IR and Raman also, like that. In the issues pane, it reports no problems, so we can finish, and we will overwrite a little rehearsal project file I did some hours ago. And now we're inside main SIMCA, and we can see that we have now 4 data sets imported. We have the Y data, and we have the different spectral measurement data. And we can also choose to plot these data. I will do that very, very shortly. Now, these data are the unpreprocessed data. So before we do anything, we will apply spectral filters. Under the data tab, we have the spectral filters. We will run SNV to align with the original publication, and we will not do it on the Y block, but on the NIR data. In the dialog, we can then select which samples in which wavelength regions we would like to involve in the SNV. We will use all samples and the full data set, all wavelength regions, or all wavelength variables in this So we say finish. We do the same thing with the IR data, use all data, the whole data set. And we do again the same thing with Raman. As you see, there are a number of available spectral filters, derivatives, MSC, SNV, and lots of other things. You can also do wavelet compression and denoising. And filters can also be combined in various ways. That is called chaining, and up to 4 filters can be chained. But right now we're proceeding with the Raman data and applying the SNV to those data as well. So now we have 3 additional data sets created. We have now, in addition to the original spectral data, also the NIR data, SNV pre-processed, the IR data, SNV pre-processed, and the Raman data, SNV pre-processed. And now we can, for instance, for the NIR data, compare original spectra with pre-processed spectra. And then we go to the data tab again using the spectra button, calling for the NIR original spectra and the SNV pre-treated spectra, and we can then combine them. And now to the left we have the SNV pre-treated data, and we can see how they are much better aligned following this pre-processing. Now comes the next stage when we will start to build models, and we have a number of data sets from which to pull out data, making up the basis for our models. And in order to tell Simca from which data sets to pull out the data, we go to the new command in the workset group, and we will first make a model between the Y block and the SNV pre-treated NIR data. We can go to the variables tab and say that the different proportions of lambda, kappa, iota, mu, and nu, these are the Y variables. So we will assign them the role Y. And then the SNV data, spectral data, are the X variables. We will do one more change, and that regards to the scaling of the SNV pre-treated spectra. And we will change from the default scaling of unit variance to just centering only. That is a good thing to do. So now we have centered the spectral data. We will not change the scaling for the 5 Y variables. They have very different proportions and different standard deviations. So using unit variance scaling on those makes sense. The model type to run is the auto PLS model, and we will use AutoFit and calculate that model. Here we now see the project window. We have information on the model, and I will now show you how you can change the model title. I'm changing the model title, NIR versus Y block, for instance. And remember, as I told you, that this information will be part of the naming structure. It will be reproduced when naming the hierarchical models. When I have that line in the model window highlighted, I now click on the right mouse button and select hierarchical base model. And this is the trick to open up the Pandora's box into the hierarchical modeling setup inside the Simca software. I click on that choice, and now I have a choice what sort of base variables I would like to create. I will use the scores and the Y orthogonal scores, for instance. When I say OK, we have now created a new data set with exactly those 5 score vectors or 6 score vectors. There were 4 predictive and 2 orthogonal. If I now want to make a top-level model, I can go to the work set and say I work with the hierarchical data, and let's say the Y block, and just make a PCA model. Now this, I emphasize, this model is a nonsense model. It's not a real model, you can say. I'm just showing you how you will get a top-level model. You see now the letter T is turned on here because we involved hierarchical base variables in a new model, and then this becomes the top-level model. I will not compute this model. I just wanted to use this project to show you how you get the B and the T. Now, because the calculations, the full set of calculations in the Carrageenan dataset is quite elaborate, I have prepared another SIMCA investigation project with this dataset where I have 5 models prepared already. And you can see the naming convention here, that we have the base level model for the NIR data, base level model for the IR model, for the Raman model. And then we have the 2 top level models corresponding to the 2 trails. We have the O2 PLS top level model and the PCA top level model. And I will exemplify the PCA top level model looking into the systematic variabilities in the spectra that didn't have anything to do with the composition of the samples. So I will plot the scores for that model. I will continue to look at the orthogonal scores for the Raman model, the base level model. This is not the predictive scores, but it's the orthogonal scores on the X side, so I will select that choice. I will also plot the orthogonal scores on the X side for the IR model, and I will plot the orthogonal scores for the NIR data using the orthogonals like that. So now I have created 4 scatter plots, and I can arrange them side by side, and we have a good transparency if we have a good naming. So this model up here in the top left, that is the lower level NIR model. In the lower left part, it is the scores for the IR base level model. In the top right hand part, it is the scores for the Raman base level model, and in the lower right hand part we have the scores for the PCA top model. We here see the segregation of samples, and if we are highlighting that group, we can see that the systematic split between samples that we saw for NIR is seen partly also for IR. It is going through to the top level model, but it's not seen in the Raman model. We can now use a very convenient tool inside the SIMCA software called group to average comparison. So we will be calculating a local average for the highlighted group and compare it to the grand average. And when we do that, we get the contribution plot of this type. By default, this contribution plot is, I'm just going to zoom in a little. By default, this contribution plot is of the bar chart or column chart type. But since we're working with spectra, we might as well just convert this into a line plot. So I'm right-clicking in the plot, I select Create Plot. I will make a new plot out of the plot. I will use the line plot. And finally, I will also, instead of plotting the original, we had up to around 700 NIR variables. Instead of plotting the variable number, I will swap to the spectral information. We have a secondary variable ID. The secondary variable ID reflects the wavelength number. So we see here that we have a peak of at around 1970 nanometer, and this is in the water region, suggesting that what separate this group of samples from the rest has to do with water. It can be a moisture problem then. The other thing that we see is that it is not expressed by the Raman data at all. And the interesting thing is that we have now enabled also the NIR data to be and IR data to be well seen in the light of the very big Raman spectral block. So going back to the SIMCA software for a couple of rounding off slides, we can say that it shows that it is possible, this example shows that it is possible to compare data from different sources in a very neat way, and very interestingly so also because one block is much wider than the others. Other advantages with the hierarchical scenario is that different observations can be outliers in different base level models, and we don't really need to start to delete all the measurement for one sample. We can have one sample to be outlier in one model, but still be part of the total model. We have seen in the other example that the top level loading plot is much less crowded than the corresponding loading plot for a PSA model based on all variables. And by combining also O2 PLS with the hierarchical modeling scenario, it is possible to find out redundant information and complementary information in the different data sets. If we look at the hierarchical modeling as such, it has a number of positive features. We have this zoom in, zoom out capability. It means that we will focus on the right variables at each level. And because we can do that, we don't have really to delete variables, because variables that are uninformative, whatever information they represent, that will be left behind us on the lower level when we move up to a higher level. We have seen also how this is an interesting alternative to block scaling. It was not until the advent of the hierarchical modeling that we had a good alternative to block scaling. So block scaling was then used to downweight very wide blocks in order to make smaller blocks being possible to see in the models. We can also use the hierarchical tool or tool set as a way to filter data, and then this is based on the residual base level variables. So consider a scenario where you have a Y variable that expresses undesirable features in your data. So it can be a machine speed, or in QSAR modeling, it can be the molecular weight of the molecules or whatever. There is something having a strong signature on all the data, and you wish to look beyond that. Then you could conceivably use the hierarchical setup as a filter by placing what you don't want as the Y, then apply PLS or OPLS. The residual matrix, E matrix of that model will then be laundered or filtered X data free of the undesirable signature, so to say. We can also use the hierarchical modeling framework as a way to conceptually deal with missing data and outlier handling, and I have more on that on the next slide. And also, if you want to work with principal component regression inside the Simca software, you will use or would use the hierarchical setup. You would calculate the number of principal components on your X block, take those score vectors and make them hierarchical base variables, and on the top level model then use PLS and fully exhaust that X block. That would be principal component regression. I have mentioned that this might be a workaround for missing data and outlier handling. In case you have a lot of missing data, conceivably you could block all the variables where you're missing data into one block, and then have other blocks where you have more present data, and try to at least a bit alleviate the impact of the missing samples. And in a similar way, you could also argue that you could handle outliers. Some samples are outliers in some models, but they can still be present in the top level. Then finally, a few words about the geometric suite. The objective with the whole tool set in making up this suite is to help our users to see what others don't. And we can use the suite for different data analytical questions. We have, first of all, we can say the two very early stages of reactive data analysis. We had a descriptive situation where we try to find out what has happened in the past. We have the diagnostic scenario where we try to understand why things happen that happened in the past, why they happen. Finally, we have the two more proactive stages of predictive data analytics and prescriptive data analytics, where we try to figure out what could happen in the future and what should we do to make a certain thing happen, or maybe even more importantly, how should we act to avoid an issue to happen. So the tool set making up the geometric suite is really flexible and versatile, and the whole goal with the geometric suite is that we want to help our clients and users to investigate the data, find the golden nuggets, capitalize on the golden nuggets by understanding how to change a little and thereby grow a lot. And with these words, I thank you all for your time and attention.